we got to spend this time trying to finish up chapter 14. We're going to spend today, we're going to spend Thursday, and then in lab, probably what we're going to do is check out, and if we have to finish up anything, then we'll finish up anything, but hopefully we can finish. We've been talking about acids and bases and what they are, and there's two different definitions. You pick which one is most convenient to use in your situation. Okay? An acid is something that will increase one of two things. It'll increase in your solution the amount of free hydrogens present, or else the amount of hydronium ions present. Remember, those are the same thing. We can count them as the same. A hydronium ion is H3O positive. That means a hydrogen is hooked onto a water molecule. Another way to define an acid is using Bronsted-Lowry's theory. The first one was Arrhenius' theory. This is Bronsted-Lowry. They say that an acid is something that, well, doesn't just increase the concentration of hydrogens. More specifically, it is a molecule that can donate a hydrogen. Okay? And in a chemical reaction, it will get rid of its hydrogen. So it's very similar but subtly different. With regard to bases, Arrhenius bases are those substances who, when you put them in a solution and you look at the solution, you increase the amount of hydroxides present. Now, that's good and it works, but the problem is if you look at the actual molecule, there's a way to always increase, with bases, they'll increase the amount of hydroxide present, but it could be, what if you got something like ammonia that doesn't even have hydroxide on it? And when you put it in a solution, where does that hydroxide come from? So Arrhenius' definition doesn't really explain that very well. So Bronsted-Lowry will say, a Bronsted-Lowry base is something that, instead of just focusing on hydroxides, they will say it is a compound that has the ability to absorb and take in hydrogens. Okay? So that's the difference between these definitions. Now with Bronsted-Lowry, this helps us a little bit more in terms of keeping track of things. Before long, there's going to be like a family reunion that's going to come in, and they're going to take up that whole table, and there's going to be potato salad and a tub of Coke and everything over there. So, unbelievable. Now I'm hungry. I'm just getting. I'm whiffing all this food that's coming my way. I'm getting distracted. All right. Well, what Bronsted-Lowry will allow us to do is take a look at it from a chemical equation perspective and try to figure out what's given up to what's taken what, and that kind of thing. So that's where we're headed with this. And allows us to look at reactions in a reversible way, like back the other way rather than just unidirectional. But anyways, this is a lot of crazy letters, but the point of this is, take a look. HA just means it's an acid. The A can represent anything. H because it's got a hydrogen on it. A B is a base. It's going to be something that's going to take on. Now, there's a cation that's missing here. It could be anything that's positively charged. It's just left off because I'm just trying to illustrate a point. So whatever ion this is can act as a base. In other words, when it reacts with this, what's going to happen is that hydrogen is going to move over and go next to that B. Okay? And that means that it has acted like a base. It has accepted a hydrogen. And the fact that that one gave off, this guy here gave off his hydrogen, means that it is going to be an acid by definition, by Bronsted-Lowry definition. So we look at the other side of the equation, and we see that that has happened. We see that this guy lost his hydrogen and thus was an acid. This was an acid. Lost its hydrogen. This picked up a hydrogen, so now this is a base. Okay? This acted as a base. Now, these guys right here are not. These are different. These are different than what's going on over here, okay? Now take a look. I want you to notice that if we reverse this reaction, what the base has become, is something now that has an H that can, in the other direction, be an acid. Okay, if we flip this arrow around, we reverse this. These are called conjugate pairs. I'm going to talk about that. Okay, all right. I'll show you what I mean. Conjugate pairs means basically this: what was your acid becomes your base. What was your base becomes your acid once the chemical equation is over. These are called conjugate pairs. Let me show you an example. Okay. instead of using these generic terms, let's use a real one here. Okay, here's formic acid reacting with water. Remember, I said water swings both ways. It's amphoteric. Okay, it can be a base or an acid depending on what you're using it for. In this particular case, it's going to be a base. All right. Think of to conjugate, or think of like conjugal visit, or whatever it is that makes you put yourself in the right place. Conjugate means to form a pair, come together, that kind of thing. When we talk about conjugate acid-base pairs, we're talking about these pairs. Something on the right side that's related to something on the left side of the equation. Okay, now let me show you what I mean. Take formic acid. Remember how we said organic acids? This hydrogen is the one that's going to go off. This one is going to be stuck to the carbon. It's not going to be the ionized hydrogen. Okay, so here's our hydrogen. This makes this an acid, okay, because of its chemical properties. It's going to end up giving this up. And in this case, you're going to see that water is going to act like a base. According to Bronsted-Lowry, it will take in a hydrogen ion. So let's look at the other side of the equation. Okay? If you have this guy who has lost its hydrogen ion, here's what you have left, right? CHO2 negative. That means this guy's out there floating around somewhere. What happened? It hooked up with the water, and when it did, it formed a hydronium ion. Okay? Now, what happened? I want to make sure you understand this. This is the acid. This is the base. What formed on the other side? Your acid will always turn into what's called a conjugate base. And your base will always turn into what's called a conjugate acid. Now think about this, and it makes sense. If you have this, and you have lost a hydrogen, it is no longer the acid anymore. Right? It has lost its hydrogen. Does it have the ability to gain a hydrogen back chemically? Sure it does. So since it has that ability, it has become now what's called a conjugate base. Now here's what you'll find. Let's say this was a really, really strong acid. What does a strong acid mean? It has the ability to do what? Break up very easily. Okay, so something that is a very strong acid. Okay, if this were a strong acid, and that means it breaks up very, very easily. So do you think that the attraction, the bond between hydrogen and this anion is a strong one or a weak one in a very strong acid? It's very weak because it falls apart very easily. All right? So do you think it wants to pick up a hydrogen very well once it loses it? No. So here's what we're getting at. A strong acid probably has what kind of conjugate base? A strong one or a weak one? A weak one. Okay? Because by virtue of the fact that it's an acid, it falls apart. If it's a strong acid, that means it falls apart very easily. That means the bond that's holding this to this is a pretty weak one. Okay? So that means that it's very unlikely that when this ion forms, it's going to want to hoard back hydrogens and stuff them together and be a good base. Remember, a base draws in hydrogen and locks it up. So that means that a strong acid will have a very weak conjugate base. That makes sense. Look at the base. The base is what accepts hydrogens. This hydrogen went here to form hydronium. This went from base to conjugate acid. Now it's got an extra hydrogen that it can give off. It's going to be a pretty weak if this was a strong base, right? A strong base is going to yield a very weak conjugate acid. A weak base would yield a strong conjugate acid. Now, why would that be? If you have a very weak acid or a weak base, okay, that means they don't want to break up. They want to stay together. So that means that, for example, if this was a really, really weak acid, that means they like to stay together. They don't want to break up. So when this does form, it's going to want to reattach itself to its hydrogen, so it's going to become a very strong conjugate base. So a weak acid will have a very strong conjugate base. A strong acid will have a weak conjugate base. Okay? So you should be able to look at an equation, let's look at this one down here, and figure out your pairs. You should be able to label the acid, the base, the conjugate acid, and the conjugate base. Okay? So let's look here. We've got water and ammonia. And according to our reaction, we get hydroxide ions and ammonium ions out of this. Okay?